Neptune is 30 astronomical units from the Sun. 30 astronomical units, 30 times the Earth-Sun distance, about 4.5 billion kilometers. Light from the Sun takes about 4 hours to reach Neptune. A spacecraft launched from Earth takes 12 years to get there. This seems very far. It is not the edge. Beyond Neptune's orbit begins a region that most people have never seen, described even in the most general terms. A region that is not simply distant emptiness, but a structured, populated, physically active domain that we are only beginning to understand. Beyond Neptune lies the Kuiper Belt, a ring of icy objects extending roughly from 30 to 50 astronomical units. Beyond that, the scattered disk, a region of even more distant and eccentric objects. Beyond that, the hypothetical outer Oort Cloud, a reservoir of comets extending to tens of thousands of astronomical units. And possibly, even farther, objects we are only beginning to suspect exist. This space is hostile. Not in a metaphorical sense, in a literal one. It is cold to a degree that makes a thermometer a useless instrument. It is dark enough that the Sun is just another bright star, noticeably bright, but not enough to provide warmth or normal illumination. It is filled with objects moving in regimes inaccessible to most of our experience. Orbital periods of thousands of years. Orbits so elongated that an object spends most of its life in the darkness of the outer system and only a brief moment near the warmth of the Sun. And it is full of surprises. Objects that do not fit existing models. Dynamical anomalies pointing towards something still unknown to us. Possibly an entire planet not yet discovered. Tonight we will travel beyond Neptune's orbit honestly and specifically, not as a journey through beautiful pictures, but as an exploration of one of the least understood regions of our own solar system. If the night is long, stay. Let us begin with the Kuiper Belt, the first structure we encounter just beyond Neptune, and what it actually is physically. In 1992, astronomers David Jewett and Jane Liu discovered the first Kuiper Belt object, a body designated 1992 QB1. It was a small, dark object, about 200 kilometers in diameter, at a distance of roughly 44 astronomical units from the Sun. Before this, the existence of the Kuiper Belt was hypothetical, proposed independently by Kenneth Edgeworth in 1943 and Gerard Kuiper in 1951 as a possible source of short-period comets. 1992 QB1 confirmed that there was something real beyond Neptune. Since then, more than 2,500 Kuiper Belt objects have been confirmed by observations. Estimates of the total number of objects larger than 100 kilometers in diameter, on the order of 100,000. Objects larger than a few kilometers, possibly hundreds of millions. This is not empty space. This is a very sparse but genuinely populated ring of bodies. The composition of these objects, a mixture of ices and silicates, not only water ice, at such distances from the Sun, methane, ammonia and carbon monoxide have frozen into solid bodies. Temperatures in the Kuiper Belt are about 40 to 50 Kelvin, approximately minus 230 degrees Celsius. At this temperature, most substances that at Earth conditions are gases are solid or liquid ices. Kuiper Belt objects are divided into several dynamical classes. Classical Kuiper Belt objects, also called cubewanos after the name of the first discovered 1992 QB1, are on low eccentricity orbits in the range of 42 to 48 astronomical units. They interact little with Neptune gravitationally. This is the most stable population of Kuiper Belt objects. Their orbits are relatively stable on long timescales. Resonant objects on orbits in orbital resonance with Neptune, the most numerous, Plutinos, are in 2 to 3 resonance with Neptune. This means that for every 3 orbits Neptune completes around the Sun, these objects complete 2. Pluto is the most well-known Plutino. It is this resonance that stabilizes its orbit, despite the fact that it crosses Neptune's orbit. Scattered disk objects have highly eccentric and highly inclined orbits. Their perihelions, points closest to the Sun, are often near Neptune. They interacted with Neptune in the past and were scattered onto their current orbits. These objects are the most dynamically active and may be a source of short-period comets. Let us now talk about Pluto, the most famous object in the outer solar system, and what we actually know about it after the New Horizons mission. Pluto averages about 39.5 astronomical units from the Sun, though its orbit is quite eccentric. At perihelion, it approaches to 29.7 astronomical units, closer than Neptune, and at aphelion, it recedes to 49.3 astronomical units. Before 2015, Pluto was for us only a spot of light, even in the most powerful telescope. A blurred point with indeterminate features. We knew its size, diameter about 2,377 kilometers, slightly smaller than the Moon. Its moons, Charon and 4 smaller ones. Its atmosphere, thin, primarily nitrogen. But surface details remained beyond the resolution of any telescope. On July 14, 2015, the New Horizons spacecraft flew past Pluto at a distance of about 12,500 kilometers. In the few hours of the flyby, we received more information about Pluto than in all the preceding decades of observation. What was revealed exceeded all expectations. The Tombaugh Regio, informally called the heart of Pluto for its shape resembling a heart, a huge white plain roughly 1,000 kilometers across. The official name of the western portion, Sputnik Planitia. It is filled with nitrogen ice of frozen molecular nitrogen, N2. This nitrogen ice is not passive. It slowly convects. Cells of nitrogen ice several kilometers across slowly overturn like boiling liquid, only billions of times more slowly. Heat from Pluto's interior drives this convective flow. Ice rises from depth, reaches the surface, cools, and sinks back down. Geological activity is occurring on Pluto. On a small, icy dwarf planet 40 astronomical units from the Sun, processes are taking place that require internal heat. Mountains. On the edges of Sputnik Planitia rise icy mountains 2 to 3 kilometers high, made of water ice. Water ice on Pluto is so hard at temperatures around 40 Kelvin that it behaves like bedrock, strong enough to support mountain ranges. The atmosphere. Pluto has a thin atmosphere of nitrogen with admixtures of methane and carbon monoxide. Surface pressure about 10 to 15 pascals. For comparison, air pressure on Earth at sea level about 101,325 pascals. Pluto's atmosphere is roughly 10,000 times thinner than Earth's. This atmosphere is dynamic. Nitrogen ice on Sputnik Planitia evaporates where it is warmed by the Sun, slowly but continuously. Gaseous nitrogen rises into the atmosphere, is carried by winds, and again condenses in cooler regions. This creates a slow atmospheric cycle, analogous to the water cycle on Earth, but with nitrogen at cryogenic temperatures. Organic compounds. The surface of Pluto is largely covered with dark reddish-brown organic compounds, tholins. These are complex hydrocarbon molecules that form when methane and other simple hydrocarbons are exposed to ultraviolet radiation and cosmic rays. Tholins on Pluto, chemically complex compounds containing carbon, hydrogen, oxygen, nitrogen. Pluto is not a geologically dead world. It is an active system with geological processes, atmospheric cycles, and a chemically rich surface. This was a revelation. Let us now talk about Charon, Pluto's largest moon, and what studying it reveals about the nature of the system as a whole. Charon has a diameter of about 1,212 kilometers, roughly half Pluto's diameter. This is an unusually large ratio. Most planets have satellites significantly smaller than themselves. The Moon is about 27% of Earth's diameter, which is already unusually large. Charon is about 51% of Pluto's diameter. The Pluto-Charon system is sometimes described as a double dwarf planet. Charon and Pluto are in mutual tidal lock. Both bodies face one side toward each other and both rotate synchronously. The orbital period of the system is about 6.4 Earth days. Charon's surface is completely different from Pluto's. No bright nitrogen ice, no orange tholins. Instead, a greyish-bluish surface of water ice, a large impact crater, Scio, and something completely unexpected, an enormous dark reddish polar cap, informally called Mordor. This reddish cap on Charon's pole consists of tholins, the same organic compounds as on Pluto. But how did they get there? Charon has no significant atmosphere of its own that could produce tholins in situ. The hypothesis: gaseous methane escaping from Pluto's atmosphere freezes on Charon's cold pole, which is in polar night during winter for decades due to the tilt of the system's axis. The frozen methane is then exposed to ultraviolet and cosmic rays and is converted into tholins. Pluto's pole paints its moon's pole, chemically contaminating it by exporting atmospheric components. This means Pluto and Charon are a chemically coupled system, not just gravitationally bound bodies, but a system where material is transferred from one body to the other. Let us now talk about other large objects in the outer solar system, about what, besides Pluto, falls into the dwarf planet class, and what their study has revealed. Eris, discovered in 2005. It was its discovery that triggered the reclassification of Pluto's status, because Eris turned out to be practically the same size as Pluto, diameter about 2,326 kilometers versus 2,377 for Pluto, but significantly more massive, about 27% more massive. If Pluto is a planet, then Eris is also a planet, and Eris is just one of many large objects in the outer system. In 2006, the IAU introduced the category of dwarf planet and reclassified both Pluto and Eris, along with Ceres in the asteroid belt. Eris is at a distance of roughly 38 to 97 astronomical units from the Sun. Its orbit is very eccentric, with a period of about 559 years. Currently, it is near aphelion, its farthest point from the Sun. Eris's surface is unusually bright, albedo about 0.96. It reflects 96% of incident light, while Pluto reflects about 0.72 and the Moon about 0.12. Such high albedo means a fresh, uncontaminated icy surface. Likely, the surface is periodically renewed when Eris is at perihelion. Volatile ices evaporate from the surface and then refreeze as it moves away from the Sun. Haumea, a dwarf planet in the Kuiper belt with several unique characteristics. First, its shape. Haumea rotates very rapidly, one complete rotation in about 3.9 hours. This is so fast that centrifugal force significantly deforms the object. Haumea has the shape of an ellipsoid, elongated like an American football, with axes approximately 2,322 by 1,704 by 1,138 kilometers. This is the most elongated large body in the solar system. Haumea has rings, discovered in 2017 through stellar occultation. Rings around a dwarf planet in the Kuiper belt. Another example that rings are not a monopoly of gas giants. Makemake, a dwarf planet approximately 1,430 kilometers in diameter. Surface covered with methane and ethane ice. Has no detected atmosphere under normal conditions, unlike Pluto. Quaoar, an object about 1,086 kilometers in diameter. In 2023, it was discovered that Quaoar has a ring, but an unusual one. The ring is located at more than 2 Roche limits, that is, farther than the distance where rings normally break up material before it can coalesce into moons. This contradicts standard ring models. Why Quaoar's ring has not coalesced into a moon, an open question. Let us now talk about the scattered disk, the region beyond the Kuiper belt that is the least understood of the main structures of the outer solar system. The scattered disk is a population of objects with highly eccentric orbits. Their perihelions are usually near Neptune's orbit, 28 to 35 astronomical units, but their aphelions reach hundreds of astronomical units. These objects were scattered by Neptune's gravity. In the past, they interacted with Neptune and received an impulse that transferred them to their current elongated orbits. The most well-known scattered disk object, Sedna. Sedna was discovered in 2003 by astronomers Michael Brown, Chad Trujillo, and David Rabinowitz. Distance from the Sun at discovery, about 90 astronomical units. Sedna's orbit is one of the most elongated in the solar system. Perihelion about 76 astronomical units, aphelion about 937 astronomical units, orbital period about 11,400 years. This is important. Sedna's perihelion, 76 astronomical units, is significantly farther than Neptune. Neptune cannot directly gravitationally interact with Sedna at its current perihelion point, too far. The standard picture of objects being scattered by Neptune does not explain why Sedna's perihelion is so far from Neptune. This is an anomaly. Several hypotheses have been proposed to explain Sedna's perihelion. One of the most discussed, in the early solar system, the Sun was part of a stellar cluster. Gravitational interactions with passing stars in this cluster could have pushed the perihelions of some objects farther, forming an orbit like Sedna's. After the cluster dispersed, these objects retained this enlarged orbit. Another hypothesis, the existence of an undiscovered massive body, a planet or superplanet in the outer solar system, that gravitationally affects objects like Sedna and explains their unusual orbits. Let us now talk about the specific evidence pointing toward the possible existence of a yet undiscovered massive planet in the outer solar system, about the Planet 9 hypothesis. In 2016, astronomers Konstantin Batygin and Michael Brown from Caltech published a paper showing that the orbits of 6 known extreme scattered disk objects, objects with very large aphelions, have a statistically anomalous clustering. Specifically, the arguments of perihelion and longitudes of ascending node of these 6 objects are grouped close to each other, as if they all pointed in the same direction in space. The probability of such a clustering occurring by chance, about 0.007%, In other words, if object positions are random, the observed clustering should have occurred only in one case out of 15,000. What could cause such clustering? Batygin and Brown proposed a massive unobserved body, a planet, on a distant elongated orbit. Their calculations suggest an object with mass of about 5 to 10 Earth masses on an orbit with perihelion of about 200 to 350 astronomical units and aphelion of about 600 to 1,200 astronomical units. Orbital period from 10,000 to 20,000 years. This is what became known as Planet 9. Why has it not been found yet? At the predicted size and distance, Planet 9, if it exists, is probably currently near aphelion. An object of 5 to 10 Earth masses at a distance of 700 to 1,000 astronomical units would be extremely faint, about magnitude 22 to 24. This is accessible for large professional telescopes, but only if you know exactly where to look. And the area of sky that needs to be searched is large. Active search programs, including the Subaru Telescope, Magellan, and the upcoming Vera Rubin Observatory Legacy Survey of Space and Time, LSST, are underway. Planet 9 has not been found yet. This does not rule out its existence. It means that if it exists, it is located where it has not yet been searched with sufficient sensitivity. Alternative explanations for the orbital clustering are also being discussed. The clustering may be an observational bias. We discover scattered disk objects not uniformly across the sky, and the clustering may reflect the non-uniformity of our observations. Some authors argue that when observational biases are accounted for, the statistical significance of the clustering decreases or disappears. The debate continues. This is a genuine open scientific problem, not a closed question. Let us now talk about the specific physical conditions that make the outer solar system beyond Neptune so extreme, about temperature and what it means to exist at 40 Kelvin. 40 Kelvin, minus 233 degrees Celsius, about 40 degrees above absolute zero. At this temperature, water, absolutely solid ice, harder than most earthly metals under ordinary conditions. At 40 Kelvin, water ice is a rigid, crystalline substance with strength comparable to granite. Nitrogen, solid. The melting point of nitrogen is about 63 Kelvin. At 40 Kelvin, nitrogen is frozen into crystalline form. This is the ice that covers Sputnik Planitia on Pluto. Carbon monoxide, solid. Methane, solid. Argon, solid. Virtually all substances that at room temperature are gases, at 40 Kelvin are solids. Oxygen, solid. If oxygen somehow reached the surface of a Kuiper belt object, it would immediately freeze into a bluish crystalline ice. Thermal motion of molecules is minimal. Chemical reactions that at ordinary temperatures proceed quickly at 40 Kelvin essentially stop. This means the chemical composition of Kuiper belt objects is preserved in the state in which it formed at the formation of the solar system 4.6 billion years ago. These objects are chemical time capsules. This is precisely why studying the composition of Kuiper belt objects is so important for understanding the early solar system. They have preserved the original chemical diversity of the disk from which the planets formed. Let us now talk about a specific phenomenon that occurs on the surfaces of outer solar system objects over billions of years, about radiation darkening and space weathering. Kuiper belt objects are constantly exposed to galactic cosmic rays and solar ultraviolet radiation. Though greatly weakened at such distances, solar light intensity decreases proportionally to the square of distance, and at 40 astronomical units is about 1/1600th of Earth's. This radiation is sufficient to produce chemical changes in the surface layer. Ionizing radiation breaks molecular bonds. Simple molecules, water, methane, ammonia, carbon monoxide, reorganize into more complex ones. Tholins form, those same dark reddish organic polymers we saw on Pluto and Charon. Over time, the surfaces of Kuiper Belt objects darken and redden. This explains why many Kuiper Belt objects have a reddish colour. They carry on their surfaces accumulated radiation-processed organic compounds formed over billions of years. But there are exceptions. Some objects, for example Eris with its extremely high albedo, have fresh, bright surfaces. The explanation? For objects with more eccentric orbits that periodically approach the Sun, volatile ices evaporate during heating and then refreeze when moving away from the Sun. This process regularly renews the surface, replacing the darkened surface layer with fresh ice. This means that an object's colour in the Kuiper Belt is a kind of history of its orbital evolution. Red, old preserved surface. Light grey or white, recently renewed surface. Intermediate shades, complex history of alternating heating and cooling. Let us now talk about the specific object that is one of the most mysterious in the Kuiper Belt, and that points to formation processes we do not yet fully understand. About Arakoth. Arakoth, official designation 2014 MU69, was the second object visited by the New Horizons spacecraft after Pluto. The flyby took place on January 1, 2019, at a distance of about 3,500 kilometers from the surface. This was the most distant object in the solar system visited by a human-made craft at that time, about 44 astronomical units. What New Horizons saw was a revelation. Arakoth is a contact binary, two bodies joined at a contact point. The larger lobe, informally called Ultima, is about 22 by 20 kilometers. The smaller, Thule, about 14 by 14 kilometers. They are connected by a thin neck. Arakoth's shape resembles a snowman, but what makes it truly unique is how exactly the two components merged. In the standard scenario of two objects colliding, the collision occurs at high speed. High-speed collisions shatter bodies or create complex mixtures of fragments. Arakoth shows no signs of impact disruption. The shape of the objects, both lobes flattened and approximately equally oriented in space, their rotation axes are parallel, no signs of deformation from impact. This suggests the two components of Arakoth did not collide in the ordinary sense. They slowly fell toward each other from nearly identical orbits, approaching at a negligible relative velocity, probably less than a few meters per second. This is called gentle accretion, or formation through cloud collapse. The mechanism. In the early solar system, rather than individual particles colliding and sticking, some groups of particles formed gravitationally bound clouds, swarming clusters that slowly collapsed into objects. If there were two centers of condensation in the cloud, two objects formed side by side from the same material and then slowly approached. Arakoth is the first direct evidence of this formation mechanism. Its study changed our understanding of how exactly the small bodies of the solar system formed in the Kuiper Belt. Arakoth's surface is reddish-brown, tholins, an old surface frozen in its state of formation 4.6 billion years ago. Arakoth has never come close enough to the Sun to renew its surface. Its orbit is nearly circular at 44 astronomical units. It is literally a sample of primary solar system material, preserved unchanged. Let us now talk about the specific phenomenon that connects the outer solar system to our everyday lives, about comets and where they come from. Comets, bodies composed primarily of ice and dust, are visible from Earth when they approach the Sun, and their volatile components evaporate, creating a tail. Bright comets are one of the most impressive phenomena of the night sky. Comets are divided into two main types by orbital period. Short period comets, orbital period less than 200 years. Halley's Comet, with a period of 75 to 76 years, is the most well known. These comets originate from the Kuiper belt and scattered disk. Interactions with the outer planets, primarily Neptune and Jupiter, transfer them to shorter orbits passing through the inner solar system. Long-period comets, orbital period more than 200 years, often thousands or millions of years. Comet Hale-Bopp of 1997, with an orbital period of about 2,520 years, is a famous example. These comets originate from the Oort Cloud. The Oort Cloud, a hypothetical spherical shell of icy bodies surrounding the solar system at distances of about 2,000 to 200,000 astronomical units. This distance is roughly 1 light year, about a quarter of the distance to the nearest star, Alpha Centauri. The Oort Cloud has never been directly observed. Its existence is inferred from the orbits of long-period comets. When a long-period comet comes in from deep space, analysis of its orbit shows it originates from distances of tens of thousands of astronomical units. These distances correspond to the hypothetical Oort Cloud. What disturbs the orbits of bodies in the Oort Cloud and sends them into the inner solar system? Several mechanisms. Gravitational perturbations from nearby passing stars. Over billions of years, many stars have passed close enough to the solar system to disturb outer bodies. The gravitational tidal effect of the galaxy itself. The Milky Way creates tidal forces at such distances that slowly perturb Oort Cloud orbits. Collisions between Oort Cloud objects. An interesting conclusion. The Oort Cloud is a kind of archive of the early solar system. Bodies in it formed near the Sun, but were ejected to these distant orbits by gravitational interactions with the forming gas giants, primarily Jupiter and Saturn. By studying the composition of comets from the Oort Cloud, we study the chemistry of the early inner solar system preserved in these bodies for 4.6 billion years. Let us now talk about a specific modern discovery that is one of the most significant in outer solar system astronomy in recent years, about interstellar objects passing through our solar system. In October 2017, Robert Weryk of the University of Hawaii discovered an object in Pan-STARRS telescope data. Designation 1I/2017 U1. Official name Oumuamua. This was the first confirmed interstellar object, a body arriving from beyond our solar system. Oumuamua's orbit was hyperbolic with eccentricity about 1.2. The object came from the direction of the constellation Lyra, passed by the Sun, perihelion about 0.26 astronomical units, closer than Mercury, and flew back out into interstellar space. This alone was an exciting discovery, but then the strangeness began. As Oumuamua moved away from the Sun, it showed atypical brightness trends. Its brightness varied with amplitude significantly greater than known asteroids or comets. This spoke of an object with very non-standard proportions, possibly flat, more like a pancake or wafer than a sphere or cylinder. Moreover, Oumuamua showed non-gravitational acceleration.
That is, it moved slightly faster than expected under the gravitational influence of the Sun alone. This deviation is small but significant. In comets, this acceleration is explained by the reactive thrust of evaporating gases. When volatile components of the comet are heated by the Sun and evaporate, they create a weak reactive impulse. But no characteristic comet tail or coma was observed for Oumuamua. This generated many hypotheses. One of the most discussed, belonging to Avi Loeb of Harvard, is that the object is an artificial light sail created by an extraterrestrial civilization. This hypothesis received significant media attention. Scientific consensus leans toward less exotic explanations. Perhaps Oumuamua was a fragment of a planetesimal from another star system composed primarily of molecular hydrogen, which evaporated invisibly to our instruments but provided non-gravitational acceleration. Or it was a comet-like object composed of carbon dioxide with negligible or invisible coma. Or it had a shape giving significant light sail effect from solar radiation pressure. No hypothesis has been definitively accepted. The object left before we could study it sufficiently. In 2019, a second interstellar object was discovered, Comet Borisov 2I/Borisov. Unlike Oumuamua, Borisov was a clear comet with a well-defined coma and tail. Its chemical composition from spectroscopic data turned out to be surprisingly similar to ordinary comets of our solar system, a mixture of water, carbon monoxide, carbon dioxide, and other volatiles. This suggests that, at least chemically, some interstellar comets resemble our own. The building blocks of planetary systems have similar compositions in different parts of the galaxy. Let us now talk about the specific spacecraft missions that visited the outer solar system and what they revealed about the space beyond Neptune. 4 spacecraft have left or are heading out of the solar system: Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, all launched in the 1970s. Pioneer 10 and Pioneer 11 showed something puzzling, the so-called Pioneer anomaly. Both spacecraft were moving slightly more slowly than predicted by Newtonian gravity, with known gravitational sources. This small deviation, about 8.7 times 10 to the minus 10 meters per second squared, was intriguingly directed toward the Sun. For more than 10 years, the Pioneer anomaly was discussed as possible evidence of new physics, modification of the law of gravity at large distances. However, detailed analysis showed that the most likely explanation is anisotropic thermal radiation from the spacecraft themselves. The radioisotope generators emitted heat not entirely uniformly, and a small asymmetry of thermal radiation created a tiny reactive impulse toward the Sun. This effect completely explains the observed deviation. Voyager 1 and Voyager 2, these spacecraft passed through the Kuiper Belt and entered interstellar space. They did not carry specialized equipment for studying Kuiper Belt objects. They were launched when the Kuiper Belt had not yet been discovered. But their passage through this region provided data on the radiation environment, magnetic field, and plasma conditions. The only spacecraft specifically designed to study the outer solar system starting from the Kuiper Belt, New Horizons. Launched in 2006, Pluto flyby in 2015, Arrokoth flyby in 2019. After the Arrokoth flyby, the spacecraft continues moving through the Kuiper Belt. Its instruments are still working and collecting data on the radiation environment, dust, and distant objects. The spacecraft is expected to operate in science mode at least until the early 2030s. No other specialized mission to Kuiper Belt objects is in operation or in near-term plans. This means our knowledge of the Kuiper Belt remains comparatively limited. Let us now talk about a discovery that has become one of the most significant in Kuiper Belt science in recent years, about the rings of Quaoar and what they tell us about physics we did not understand. Quaoar, official designation 50,000 Quaoar,
is a Kuiper Belt object about 1,086 kilometers in diameter, discovered in 2002. It has one known moon, Waywat, about 80 kilometers in diameter. In February 2023, an international team of astronomers using data from several telescopes, including the Cheops Space Telescope, announced the discovery of a ring around Quaoar. Rings are not new to the solar system. Jupiter, Saturn, Uranus and Neptune have rings. Rings have also been found around several centaurs, Chariklo and Chiron, and around the dwarf planet Haumea. But Quaoar's ring is unusual for one fundamental reason: its location. The ring is at a distance of about 4,100 kilometers from Quaoar's center.
Quaoar's Roche limit, the distance inside which tidal forces break up material faster than it coalesces, is at about 1,750 kilometers from the center. Quaoar's ring is more than twice as far as the Roche limit. This is a problem. Standard ring theory predicts that beyond the Roche limit, material quickly coalesces into moons. Inside the Roche limit, tidal forces prevent coalescence and material remains as a ring. How can a ring exist so far beyond the Roche limit, where it should have coalesced into a moon long ago? The proposed explanation: the temperature of the ring particles. At temperatures around 70 Kelvin, which are characteristic for Quaoar at its orbit, ice becomes very elastic. Collisions between particles are elastic rather than sticky. Material in the ring does not coalesce because collisions between particles do not lead to them sticking. They bounce off each other. This prevents agglomeration into a moon even beyond the Roche limit.
If this is correct, the Roche limit for cold, icy bodies in the outer solar system is significantly farther from the body than for warm materials. This means our ring dynamics models, developed for inner solar system conditions, are not directly applicable to the outer system. This is a fundamental result. It says that ring physics depends on the temperature of the material, and that the outer solar system has its own specific regimes of material behavior without analogues in the inner system. Let us now talk about the specific comparison that gives the scale of the outer solar system, about how distances from the Sun to Kuiper Belt objects and Oort Cloud compare to the distance to the nearest stars. Neptune, 30 astronomical units. Kuiper Belt ends, roughly 50 astronomical units. Scattered disk extends to several hundred astronomical units. Sedna, at aphelion, 937 astronomical units. 1 light year, about 63,241 astronomical units. The nearest star, Proxima Centauri, about 4.24 light years, or about 268,000 astronomical units. Outer boundary of the Oort Cloud, about 200,000 astronomical units, or about 3.2 light years. This means the Oort Cloud extends to about 3/4 of the distance to Proxima Centauri. The solar system in this sense does not end at Neptune's orbit, or even Pluto's orbit. It extends to nearly half the distance to the nearest star. This is not a metaphor. Oort cloud bodies, real physical objects, are located in the region of space we normally think of as between the stars. When traveling between stars, the solar system occupies a much larger fraction of interstellar distance than we intuitively imagine. Furthermore, stellar systems in our part of the galaxy are at distances of about 1 to 5 light years from each other. If neighbouring stars also have Oort clouds extending to a few light years, the Oort clouds of neighbouring stellar systems may overlap. Material from Alpha Centauri's Oort cloud could have entered the Sun's Oort cloud and vice versa, meaning that material exchange between stellar systems through their Oort clouds is a genuinely possible process. This has implications for panspermia, the hypothesis of spreading life between stellar systems. If life, or prebiotic organic molecules, can travel in icy bodies through interstellar space, exchange between overlapping Oort clouds is a natural channel for such transport. Let us now talk about the physical reality of the darkness of the outer solar system, about what it means for illumination at these distances. At Neptune, the Sun is about 900 times dimmer than from Earth. Brightness decreases proportionally to the square of distance. 30 squared equals 900. Despite this, the Sun is still the dominant light source. From Neptune's surface, solar noon approximately corresponds to an overcast winter day on Earth. Not dark, but not bright.
But at 44 astronomical units, Arakoth, the Sun is about 1,900 times dimmer than from Earth. This would be roughly like a full moon on Earth. Noticeable illumination, but not daylight. At Sedna at perihelion, 76 astronomical units, roughly 5,800 times dimmer. This would be extremely faint illumination, darker than the deepest twilight on Earth. At 200 astronomical units, where some scattered disk objects are at perihelion, roughly 40,000 times dimmer than on Earth. The Sun at this brightness looks like an extraordinarily bright star, much brighter than any other star in the sky, but not as a disk capable of illuminating a surface. At 1,000 astronomical units, the supposed perihelion of Planet 9, the Sun is about magnitude -13. This is roughly like a full moon as seen from Earth, moon-level illumination. At Oort Cloud distances, 50,000 astronomical units, the Sun is simply a very bright star, brighter than Sirius, but not qualitatively different.
This means the entire outer solar system, beyond Neptune, is illuminated significantly less than we intuitively picture when thinking of the solar system. This is not a zone of daylight, it is a zone of gradually increasing darkness. Let us now talk about the dynamical past of the solar system, about how the current architecture of the outer regions preserves the history of planetary migration. The current structure of the Kuiper Belt is not what was there originally. The early solar system was much more populated beyond Neptune's orbit. The mass of material there was 15 to 50 times greater than the current mass of the Kuiper Belt. What happened to this material? The Nice model, developed by a group of astronomers in Nice in 2005, proposes the following scenario. In the early solar system, the four gas giants, Jupiter, Saturn, Uranus, Neptune, were on more compact orbits than today. They were in a configuration with smaller mutual separations.
Beyond them lay a disk of planetesimals, extending from about 15 to 16 astronomical units to 30 to 35 astronomical units. Over the first several hundred million years, gravitational interactions between the gas giants and this disk slowly transferred planetesimals to various orbits. Roughly 700 to 800 million years after the system's formation, Jupiter and Saturn passed through the 1 to 2 orbital resonance, 2 Jupiter orbits for every 1 Saturn orbit. Passing through this resonance triggered rapid destabilization of all gas giant orbits. Uranus and Neptune were scattered to more distant orbits. Neptune migrated outward through the planetesimal disk, scattering most of them.
The scattered objects were either ejected from the system or transferred to short-period orbits, becoming sources of the inner system bombardment, the late heavy bombardment of lunar cratering 3.9 billion years ago, or captured into resonances with Neptune, forming resonant Kuiper Belt objects, Plutinos and others, or scattered to the outer region, forming the scattered disk and Oort Cloud. The current sparse Kuiper Belt, remnant of this originally much more massive disk, 99% of which was scattered by Neptune's migration. This explains several observed facts: why the Kuiper belt is now significantly less massive than planet formation models predict, why orbital resonances with Neptune exist, why the scattered disk has the shape it has. But it also means the current outer solar system is the product of a catastrophic restructuring, not calm, gradual formation. The Kuiper belt we observe today is not a pristine, untouched region. It is the survivors after a massive scattering event. Let us now talk about what is perhaps the most profound general conclusion from everything we have discussed about space beyond Neptune, about what this region tells us about our solar system as a whole. The solar system is not static. It evolved and continues to evolve. The early system was significantly more populated in the outer regions. Gas giant migration emptied most of the primary planetesimal disk, scattering its objects throughout the system and beyond. The current sparse Kuiper belt is a shadow of its former dense structure. The Kuiper belt is now slowly losing mass through collisions, shattering objects and producing dust. Through Neptune's scattering, small objects with orbits near Neptune gradually scatter, and through supplying comets to the inner system. In billions of years, the Kuiper belt will become even less populated. Space beyond Neptune is not simply a cold, distant periphery. It is an archive of our solar system's history from its first millions of years of existence, an archive we are only beginning to read. The orbits of Kuiper belt objects carry traces of Neptune's migration. The chemistry of their surfaces reflects the primary disk composition and subsequent radiation processing. The dynamical anomalies of Sedna and similar objects point to events in the early solar system and possibly to undisclosed objects. Everything you see when you look toward Neptune's direction tonight, and cannot see because these objects are too faint, is out there, moving, changing slowly, holding 4.6 billion years of history. Let us talk about a specific phenomenon that connects the Kuiper belt to the question of life's origins, about tholins and why studying them matters far beyond the outer solar system. Tholins are a class of complex organic polymers that form when simple organic molecules, methane, ammonia, water, carbon monoxide, are exposed to ultraviolet radiation and high-energy particle bombardment. The name comes from the Greek word tholos, meaning muddy or hazy, introduced by Carl Sagan and Bishan Kare in 1979. Tholins have a characteristic dark red or brown color, which explains the reddish-brown coloration of many outer solar system objects: Pluto, Charon's polar cap, Arakoth, many centaurs, and Kuiper belt objects. Why do tholins matter for understanding life? First, tholins are complex organic molecules. Although they are not themselves biological molecules, they contain the same functional groups as biologically important molecules. In laboratory experiments, hydrolysis of tholins, adding water, produces amino acids, the building blocks of proteins. Second, tholins are widely distributed in the solar system and presumably in other planetary systems. Their presence on the surfaces of Kuiper belt objects and in comets means that simple organic precursors of life form in conditions of interstellar space and early planetary systems. Third, comets carrying tholins bombarded the early Earth. This could have delivered organic molecules, precursors to biochemistry, to the young planet before life appeared. This is one of the pathways of exogenous delivery of organic material, a scenario where the building blocks of life came from space rather than forming only on Earth. Experiments show that a wide spectrum of organic molecules forms in tholins when heated or hydrolyzed. Nucleobases, components of DNA and RNA, have been obtained in laboratory experiments with tholins. This does not prove that life originated from tholins, but it shows that material necessary for life could have been available on early Earth precisely from cometary and asteroidal delivery. The connection between the Kuiper Belt and the origin of life on Earth is real and significant. Let us now talk about the specific discovery that has most surprised scientists studying the Kuiper Belt in recent years, about what JWST found on the surfaces of Kuiper Belt objects. The James Webb Space Telescope, with its infrared sensitivity, has begun to revolutionize what we know about the surface chemistry of trans-Neptunian objects. In 2023 to 2024, JWST produced spectra of several Kuiper Belt objects in the near-infrared range, 1 to 5 microns, with resolution and sensitivity significantly exceeding anything obtained previously. An unexpected discovery. On the surfaces of several Kuiper Belt objects, JWST detected CO2, carbon dioxide, in solid phase. It had been observed in the asteroid belt and on the surfaces of some satellites of gas giants, but its presence in significant quantities on the surfaces of Kuiper Belt objects fresh information. Moreover, JWST detected features corresponding to a mixture of CO2 with complex organic compounds, tholins. This suggests that the surfaces of Kuiper Belt objects carry complex mixtures of inorganic and organic ices that formed under radiation processing over billions of years. Also detected NH3, ammonia, combined with water ice on some objects. Ammonia is interesting because it lowers the freezing point of water. A mixture of water and ammonia remains liquid down to about -100 degrees Celsius. This makes subsurface liquid layers, cryoceans, significantly more possible on Kuiper Belt objects. For the existence of a liquid phase, a significant heat source is not needed if ammonia is present in the right ratio. Heterogeneity of spectra within a single object. Different parts of the surface have different chemical compositions. This suggests a heterogeneous history of surface processing. Different areas experienced different temperature conditions or have different surface ages. All these data are only being systematically analyzed. Publications with full analysis are appearing gradually throughout 2023 to 2025. Let us now talk about Sedna in more detail, because it is one of the most scientifically provocative objects in the entire solar system, and its properties remain partially unexplained. Sedna was discovered on November 14, 2003, when Michael Brown, Chad Trujillo, and David Rabinowitz were conducting a systematic sky survey using the Samuel Oschin telescope at Palomar Observatory. Its orbital parameters are extraordinary. Perihelion 76 astronomical units, aphelion 937 astronomical units, orbital period 11,400 years, inclination to the ecliptic about 11.9 degrees. At its current distance of about 84 astronomical units, Sedna is the most distant known solar system object at or near perihelion. It is currently approaching perihelion, which it will reach around the year 2076. This means for the next several decades we have an opportunity to study Sedna at its closest approach, something that will not recur for 11,400 years. The surface of Sedna is one of the reddest in the solar system, almost as red as the red-coloured centaurs. This deep red coloration is consistent with a thick layer of tholins built up over billions of years of radiation processing, with essentially no renewal mechanism. Sedna never comes close enough to the Sun for volatile ices to evaporate and refresh the surface. The diameter of Sedna is estimated at about 995 kilometers, making it one of the larger trans-Neptunian objects, though smaller than Pluto. Sedna has no confirmed moon. This is noteworthy. Many Kuiper Belt objects have moons, and the formation of binary and multiple trans-Neptunian objects is thought to be common in the outer solar system. The absence of a detected moon for Sedna could mean it formed differently from the typical binary formation process, or that any moon is simply too faint to have been detected. The deeper mystery of Sedna remains its perihelion distance. At 76 astronomical units, Sedna's closest approach to the Sun is still far beyond where Neptune's gravity can efficiently sculpt orbits. The three hypotheses, stellar cluster encounter, planet 9, or outer Oort Cloud dynamics, all remain viable. None has been definitively confirmed. When the Vera Rubin Observatory begins operations in 2025 and accumulates data through the 2030s, it should discover additional Sedna-like objects. If there is a Planet 9 or a past stellar encounter that created Sedna's orbit, there should be an entire population of Sedna-like objects on similar orbits. Finding this population and characterizing its statistical properties would strongly constrain which formation mechanism is responsible. Let us now talk about the specific role of Jupiter in the history of the Kuiper Belt, because the outer planet that most influenced the Kuiper Belt is not Neptune, but Jupiter. Neptune is the planet that directly sculpts the Kuiper Belt through resonances and scattering. But Jupiter is the planet that set the stage for everything. In the Nice model of solar system evolution, the original planetesimal disk extended from about 15 to 35 astronomical units. Neptune migrated outward into this disk. But what triggered Neptune's outward migration? The 1 to 2 orbital resonance between Jupiter and Saturn. When Saturn's orbital period became exactly twice Jupiter's, the two giant planets began to interact strongly with each other and with Uranus and Neptune. This resonance crossing destabilized the entire outer solar system. Jupiter, the most massive, was relatively unperturbed. It barely changed its orbit. But Saturn, Uranus, and Neptune were significantly displaced. Neptune moved outward into the planetesimal disk, beginning the cascade of scattering that depleted the disk and created the Kuiper Belt we see today. This means the Kuiper Belt's current structure is a direct consequence of the orbital resonance history of Jupiter and Saturn. A different orbital history for Jupiter and Saturn, a different Kuiper Belt. A different Kuiper Belt, possibly different delivery of water and organics to the early Earth. Jupiter's influence on the outer solar system is thus profound and indirect, not through direct gravitational scattering of Kuiper Belt objects today, but through having triggered the entire dynamical evolution that created the current configuration billions of years ago. Let us now talk about something that illustrates how the outer solar system continues to surprise us, about the discovery of rings around small bodies and what it implies. Before 2013, rings were known only around the 4 giant planets. Then, in 2013, rings were discovered around Chariklo, a centaur, a body on an orbit between the orbits of the giant planets. This was the first ring system discovered around a small body. Since then, rings have been found around additional small bodies. Chiron, another centaur, 2015, Haumea, a dwarf planet, 2017, and Quaoar, a Kuiper Belt object, 2023. What does the increasing frequency of ring discoveries tell us? Most likely it tells us that rings are more common than previously thought, not unique to giant planets, but a feature that small bodies can also maintain under the right conditions. The key conditions seem to be a body large enough to have a significant gravity field, the right source of ring material, recent collisions, tidal disruption of a moon or outgassing, and physical conditions that prevent the ring material from rapidly coalescing into a moon. For the outer solar system objects, as the Quaoar ring demonstrated, the cold temperatures allow rings to exist farther from the body's centre than expected in the warmer inner solar system. The elastic properties of cold ice at 70 Kelvin allow ring particles to bounce off each other rather than sticking, preventing coalescence. This means that ring systems may be common throughout the Kuiper Belt and scattered disk. We simply have not had the observational tools to detect them. Stellar occultation observations reveal rings when they can be organized in advance, when we know an occultation is coming and can position observers to detect brief secondary dips in star brightness. The Vera Rubin Observatory will dramatically increase the catalogue of predicted stellar occultations, because it will survey the sky repeatedly and provide very precise positions for both Kuiper Belt objects and background stars. This will allow planning of targeted occultation campaigns to search for rings around many more objects. We may be at the beginning of discovering that rings are a common feature of the outer solar system, not an exception. Let us now talk about a specific aspect of the interstellar object discoveries, about what Oumuamua and Borisov tell us about the exchange of material between stellar systems. The discovery of 2 interstellar objects within 3 years, Oumuamua in 2017, Borisov in 2019, was statistically significant. It suggested that interstellar objects passing through our solar system are common. Perhaps there are several passing through at any given time. We simply had not had instruments sensitive enough to detect them in large numbers. Statistical estimates based on the detection rate suggest that there are roughly 1 to 2 interstellar objects per astronomical unit of the inner solar system at any given time. This number comes from working backward from the detection rate, correcting for the fraction of the sky being surveyed and the sensitivity of the instruments. If interstellar objects are this common, they represent a continuous exchange of material between stellar systems, material that formed around another star, entered our solar system, interacted with our planet's gravity, and left again, or, in some cases, was captured into a long-period orbit. Some interstellar material that entered our solar system in the past may still be in bound orbits, in the Oort Cloud, or in extremely long-period orbits. We would not know which objects are native to our system and which are interstellar interlopers without detailed isotopic measurements, because interstellar material would have formed in a different chemical environment and carry different isotopic signatures. This possibility that the Oort Cloud contains captured interstellar material mixed with native solar system material is scientifically fascinating, but practically difficult to test. Distinguishing native from interstellar material requires isotopic analysis of individual Oort Cloud objects, which in turn requires either a sample return mission or close flyby with a mass spectrometer. The upcoming interstellar object detection rate from the Vera Rubin Observatory, expected to find roughly 1 per year, will build enough statistics to begin characterizing the population statistically. What are the typical sizes? What are the typical compositions, insofar as can be measured from reflected light? Are there distinct populations corresponding to different stellar birth environments? These questions will be answerable within the next decade.
Let us now talk about the specific future mission concept that would most dramatically advance our understanding of the outer solar system, about what an Oort Cloud probe would need to do and why it is so technically challenging. The Oort Cloud has never been visited by any spacecraft. By definition, it cannot be. The distances involved are thousands to tens of thousands of astronomical units. At Voyager 1's current speed of 17 kilometers per second, it would take approximately 300 years to reach the inner Oort Cloud and 30,000 years to reach its outer boundary. To reach the Oort Cloud on human timescales requires either dramatically faster propulsion, speeds of hundreds of kilometers per second rather than tens, or an extraordinarily long mission timescale that extends across multiple generations. Nuclear thermal propulsion, which uses a nuclear reactor to heat propellant rather than burning it chemically, can approximately double the specific impulse, efficiency, of propulsion. This improves performance, but not enough to make Oort Cloud missions practical within a human lifetime. Nuclear pulse propulsion, the concept of propelling a spacecraft using a series of nuclear explosions behind a pusher plate, was studied in the 1950s and 1960s under Project Orion. Theoretical spacecraft could reach speeds of several % of the speed of light using this concept, making an Oort Cloud mission possible within decades. But the concept requires nuclear explosions in space, prohibited by the Partial Test Ban Treaty, and practically and politically infeasible. Laser-propelled light sails, the concept being explored by Breakthrough Starshot for interstellar travel, could in principle be scaled down for an Oort Cloud mission. A sail propelled by a powerful ground-based laser could reach a few % of the speed of light, reaching the inner Oort Cloud within a few decades. The challenge is that a tiny sail at % of light speed encounters dust and small particles that become lethal projectiles, and the communication bandwidth from such a fast-moving object at great distance is extremely limited. The practically achievable near-term missions are limited to improving our indirect characterization of the Oort Cloud through better comet surveys, tracking long-period comets as they enter the inner solar system and analyzing their compositions as proxies for Oort Cloud material. The Vera Rubin Observatory will dramatically increase the discovery rate of long-period comets. For every new long-period comet discovered, JWST can be used to obtain spectroscopic measurements of its composition during perihelion passage, when outgassing makes the nucleus chemistry accessible. Building a statistical sample of Oort Cloud comet compositions will provide an indirect census of what the Oort Cloud is made of. This is our practical path to Oort Cloud science in the near term. Not visiting it, but reading its composition through the comets it sends us. Let us now talk about what the atmosphere of Pluto tells us about atmospheric processes on small worlds, and why the physics there is relevant beyond Pluto itself. Pluto's atmosphere has a nitrogen-dominant composition with methane and carbon monoxide as minor constituents. The atmospheric pressure at the surface is about 10 to 15 pascals, about 1/10,000th of Earth's atmosphere. This atmosphere is in a peculiar dynamical state. Nitrogen ice on Sputnik Planitia sublimates where it is illuminated by the Sun, adding gas to the atmosphere. The atmospheric nitrogen circulates across the globe. In colder regions, particularly at night or at high altitude, nitrogen recondenses as frost. This sublimation-condensation cycle is the fundamental driver of Pluto's atmospheric dynamics. But here is the remarkable part. Pluto's atmosphere interacts with the nitrogen ice reservoir in a way that acts as a thermostat. If Pluto were to move slightly closer to the Sun, more nitrogen ice would sublimate, the atmosphere would become denser. The increased atmospheric greenhouse effect and albedo changes would partially counteract the warming. If Pluto moved slightly farther from the Sun, the atmosphere would thin, eventually becoming too thin to maintain this feedback.
This is a rudimentary climate feedback system on a tiny frozen world 40 astronomical units from the Sun. Not as complex as Earth's climate system, but recognizably climate-like in its feedbacks. The physics of volatile transport, sublimation of ices, atmospheric circulation, redeposition as frost, is the same physics that operates on Mars, with CO2 instead of N2, and on Triton, Neptune's moon, which also has a nitrogen atmosphere and surface ices. Understanding it on Pluto, where we have detailed topographic, compositional, and atmospheric data from New Horizons, helps calibrate models that apply to these other bodies. It also gives us a template for understanding icy worlds in exoplanetary systems, exo-Plutos, exo-Tritons, where we will never be able to land or fly by, but where understanding the general physics lets us interpret distant spectroscopic observations. Let us now talk about a specific technical achievement that made Pluto science possible, and that illustrates how mission design choices matter enormously, about the radioisotope power systems that have enabled outer solar system exploration. Solar power is the dominant technology for spacecraft power in the inner solar system. Mars rovers use solar panels. Earth observation satellites use solar panels. Even the ISS uses solar panels. At Pluto, 40 astronomical units, solar intensity is 1/1600th of Earth's. Solar panels would need to be enormous to generate useful power. A spacecraft the size of New Horizons, roughly 478 kilograms, requiring perhaps 200 watts of electrical power at Earth distance, would need solar panels with hundreds of square meters of area at Pluto distance, making the spacecraft impossibly large and heavy. New Horizons was powered by a single radioisotope thermoelectric generator, RTG, using plutonium-238. This produced about 245 watts of electrical power at launch and has decreased slowly as the plutonium decays. At Pluto distance, the RTG was producing about 200 watts, still sufficient to power the science instruments and communication systems. RTGs enable outer solar system exploration in a way that no other technology currently can. They provide constant power regardless of distance from the Sun. They do not require orientation toward the Sun, and they have no moving parts that can fail. The plutonium-238 fuel for RTGs is a byproduct of nuclear weapons production. It is not found in nature and must be artificially manufactured. For decades, NASA struggled with limited supplies of plutonium-238 as the Cold War-era production infrastructure shut down. This threatened future outer solar system missions. In the 2010s, DOE restarted production of plutonium-238 at Oak Ridge National Laboratory, though at rates slower than NASA's projected needs. This remains a strategic constraint on future outer solar system mission planning. Next-generation RTG designs, the multi-mission radioisotope thermoelectric generator, MMRTG, used on the Mars Science Laboratory/Curiosity and Mars 2020/Perseverance rovers, are more efficient and versatile. These will power future outer solar system missions. Advanced nuclear power concepts, fission surface power systems, small fission reactors for deep space, could eventually provide much higher power levels than RTGs. NASA and DOE are developing the kilopower/crusty reactor concept, capable of producing kilowatts of electrical power from a small fission reactor. Such reactors could power missions with more capable instruments, more communication bandwidth, and more propulsion options than RTG-powered spacecraft. The history of outer solar system exploration is inseparable from the history of nuclear power for space, a connection that will continue to define what is possible in this region.
Let us now talk about the observational experience available to anyone tonight, about what you can see of the outer solar system and what it represents. Pluto is currently in Sagittarius, near the center of the galaxy. Its brightness is about magnitude 14.3. This is significantly fainter than the naked eye limit, about magnitude 6.5, and requires a telescope of at least 200 to 250 millimeters aperture for reliable detection. In any realistic amateur telescope, even a 400mm one, Pluto appears as an indistinguishable point. No disk, no surface details, just a faint point among stars. The only way to confirm you are seeing Pluto is to observe it on multiple nights and note the movement. Pluto slowly shifts relative to background stars, though very slowly, fractions of an arc-minute per day. Comparing images or sketches made with an interval of several days, you can see that one of the points has shifted. That is Pluto. Nevertheless, even this faint point is an observation of a real world 5 billion kilometers away. A world with water ice mountains, nitrogen ice plains, a thin nitrogen atmosphere, and a moon more than half its own size. Beyond Pluto, farther into the darkness, Charon and Styx and Nix and Kerberos and Hydra. 4 small moons too faint for most amateur instruments. And Eris at 96 astronomical units, currently near aphelion, even fainter than Pluto despite its high albedo. And Arakoth at 44 astronomical units, about magnitude 26 to 27, inaccessible to all but the largest professional telescopes. And far beyond all of them, Sedna, slowly moving at 84 astronomical units right now, an inconspicuous point of magnitude 21 for those telescopes that know where to look. And possibly Planet 9, waiting to be discovered, or not existing. We do not know. Let us now talk about what lies at the very far edge of what we call the solar system, about the Oort Cloud as a physical structure and how we know it is there, even though we have never seen it. The evidence for the Oort Cloud's existence is entirely indirect. We have never imaged a single Oort Cloud object directly. We know it exists because of the orbits of the comets that come from it. When a long-period comet is discovered and its orbit is computed, the orbit backward in time shows where the comet came from. The most distant origins, thousands to tens of thousands of astronomical units, populate what Jan Oort in 1950 proposed as a vast spherical reservoir of cometary bodies. The distribution of original orbits of long-period comets, how their aphelia are distributed in space, is consistent with this reservoir being roughly spherical rather than disk-like. This spherical distribution is itself informative. The Kuiper belt and scattered disk are disk-like. They lie roughly in the plane of the solar system. The Oort cloud is spherical. Comets come from all directions, not preferentially from the ecliptic plane. This spherical structure is thought to result from the history of how the Oort cloud was populated. Objects were originally in the disk, in the same plane as the planets. They were scattered outward by the gas giants. When they reached the distant outer solar system, passing stars and the galactic tide randomized their orbital inclinations over billions of years, turning the original disk distribution into a spherical distribution. The same galactic tidal forces and passing stars that randomized the inclinations over billions of years continue to slowly perturb Oort cloud orbits. Some of the resulting perturbations send objects sunward. These become the long-period comets we observe. The galactic tide is a real astronomical force acting on our solar system. The differential gravitational pull of the rest of the Milky Way galaxy across the diameter of the Oort cloud is detectable and significant.
Our solar system orbits the galactic center. The gravitational gradient across the extent of the Oort Cloud exerts a small but cumulative tidal force that acts on the outermost solar system objects over millions of years.
This connection between the outer solar system and the dynamics of the Milky Way as a whole is one of the more mind-expanding aspects of Oort Cloud science. The solar system is not an isolated bubble. It is embedded in the galaxy, and the galaxy's gravity reaches into the farthest corners of the solar system. Let us now talk about something that brings all of this back to the most concrete physical level, about what the space between Kuiper Belt objects is actually like. The Kuiper Belt sounds populous when described as containing hundreds of thousands of objects larger than 100 kilometers, but the volume of space it occupies is enormous. The Kuiper Belt extends from roughly 30 to 50 astronomical units. The volume of this torus-shaped region, assuming a vertical extent of a few astronomical units above and below the ecliptic, is approximately 20 billion cubic astronomical units. 1 astronomical unit is 150 million kilometers. 1 cubic astronomical unit is therefore 150 million kilometers cubed, equals about 3.4 times 10 to the 24th power cubic kilometers.
20 billion cubic astronomical units is about 6.8 times 10 to the 34th power cubic kilometers. If there are 100,000 objects larger than 100 kilometers in this volume, each object has on average 6.8 times 10 to the 29th power cubic kilometers of space to itself. This is a cube about 880 million kilometers on a side, 6 times the Earth-Sun distance in each direction. The Kuiper Belt feels crowded when described as containing hundreds of thousands of objects. In physical reality, the average separation between objects is enormous. A spacecraft flying through the Kuiper Belt, as New Horizons did, is in essentially empty space. The probability of hitting a Kuiper Belt object by chance during a traverse is negligible. The biggest concern is not collision with large objects, but with dust and small debris produced by collisions between the larger bodies. This vast emptiness of even the populated outer solar system is one of the hardest things to communicate intuitively. The solar system, even the densest parts of the asteroid belt and Kuiper Belt, is astonishingly empty by everyday standards. The distances between objects are so vast that space travel through these regions is not navigation through a debris field, but navigation through near-perfect emptiness, with occasional objects detected by careful search. The darkness, the cold, the emptiness, these together define what the space beyond Neptune is like. Not the hostile, crowded badlands of science fiction. The quiet, cold, almost unimaginable emptiness of a region that contains enormous amounts of material relative to deep space, but almost nothing relative to any human experience of density or population. Let us now talk about the question that connects all of this to the most fundamental curiosity, about what the outer solar system ultimately tells us about whether we are alone. Tholins on Kuiper Belt surfaces. Amino acids produced from tholins in laboratory experiments. Complex organic molecules in comets from the outer solar system. Comets delivering this material to early Earth. The possibility of liquid water beneath the surfaces of Kuiper Belt objects. The exchange of material between stellar systems through overlapping Oort clouds. None of this proves that life exists beyond Earth, but all of it together builds a picture that the chemistry necessary for life, or at least for the precursors to life, is widespread in the cosmos. It is not confined to special locations. It forms naturally wherever simple molecules exist and radiation is present to process them. which is nearly everywhere. The question of whether life is common or rare in the universe is not answered by studying the outer solar system. But the outer solar system tells us that chemistry is not the limiting factor. The building blocks are available. They were available on the early Earth because the outer solar system delivered them. The limiting factors, if life is rare, must be elsewhere. Perhaps in the specific sequence of events needed to go from pre-Bartic chemistry to self-replicating molecules. Perhaps in the need for a stable planetary environment maintained for billions of years. Perhaps in something we do not yet understand. The outer solar system is one chapter in this larger story. A cold, dark, chemically rich chapter that connects the formation of our solar system to the origin of life on Earth through a chain of delivery and chemistry spanning 4.6 billion years. Standing outside on a cold, clear night, looking toward the constellation Sagittarius, where Pluto is right now, you are looking toward one of the most scientifically rich and least understood regions of the solar system. A region that preserves the chemical memory of the beginning. A region that continues to send us messengers, the comets, carrying ancient chemistry from its depths. It is dark there. It is cold beyond any earthly experience. It is vast beyond intuitive comprehension, and it is part of our solar system, part of our home, the part we have barely begun to know. Let us talk about something that reveals how interconnected the outer solar system is with the evolution of life on Earth. About the relationship between Kuiper belt dynamics and mass extinction events. The fossil record on Earth documents several major mass extinction events, episodes where a significant fraction of species disappeared in a geologically brief time. The most well-known is the end Cretaceous extinction, 66 million years ago, when roughly 3/4 of all species disappeared, including the non-avian dinosaurs. The largest mass extinction in Earth's history, the Permian-Triassic event, 252 million years ago, eliminated perhaps 96% of marine species. The causes of mass extinctions are varied and still debated. The end Cretaceous event has a clear culprit, the Chicxulub impact. But what was the impactor? The composition of the impact layer worldwide, a thin layer of iridium-enriched clay found at the Cretaceous-Paleogene boundary in rocks across the planet, is consistent with a carbonaceous chondrite composition. The specific chemistry suggests either an asteroid from the outer asteroid belt or possibly a comet from the outer solar system. A 2021 paper by Siraj and Loeb proposed that long-period comets from the Oort Cloud could be tidally disrupted by Jupiter's gravity as they pass through the inner solar system. This disruption would produce a shower of smaller cometary fragments, any of which could produce an impact similar to Chicxulub. They argued that a substantial fraction of large impact events in Earth's history could be explained by this mechanism: tidally disrupted Oort Cloud comets rather than asteroids. This is not the consensus view. Most planetary scientists attribute Chicxulub to an outer main belt asteroid. But the debate illustrates how uncertain the connection between outer solar system dynamics and Earth's impact history remains. What is not debated, the rate of large impacts on Earth over geological time has been influenced by the dynamics of the outer solar system. When planetary orbital changes or stellar passages perturb the Oort cloud, sending more comets into the inner system, the impact rate on Earth increases. Statistically, over hundreds of millions of years, Earth has experienced multiple elevated impact periods connected to these external perturbations. Our biological history, the specific sequence of mass extinctions that shaped which lineages survived and which died out, is connected to the dynamics of icy bodies billions of kilometers away. The specific timing of the Chicxulub impact, 66 million years ago, allowed mammals, which survived, to diversify into the ecological niches vacated by the dinosaurs. A different timing would have produced a different evolutionary history. We exist in part because of the specific trajectory of whatever struck 66 million years ago, a trajectory that began in the outer solar system billions of years before the impact. This is not a comfortable thought, but it is an accurate one. Our existence is contingent on the dynamical history of a region so cold and dark and remote that we have only recently begun to understand it. Let us now talk about a specific object that exemplifies the scientific richness of the outer solar system in a way that was entirely unexpected. About Triton, Neptune's largest moon, and its connection to the Kuiper Belt. Triton orbits Neptune in a retrograde direction, opposite to Neptune's rotation and opposite to the orbital motion of Neptune's other moons. This is the most direct evidence that Triton did not form with Neptune, but was captured. The most likely origin, Triton was originally a Kuiper Belt object, a large body in the outer solar system that was captured into Neptune's orbit through a gravitational interaction. The specific mechanism most commonly proposed, Triton was originally part of a binary Kuiper Belt object. When this binary passed close to Neptune, one member of the binary was captured by Neptune's gravity, while the other was ejected from the system. This binary capture mechanism can produce a bound orbit from an unbound flyby without requiring an unrealistically close passage. If Triton is a captured Kuiper Belt object, then we have actually studied a large Kuiper Belt body in detail through Voyager 2's 1989 flyby. Triton's diameter is about 2,707 kilometers, larger than Pluto. Its surface temperature is about 38 Kelvin, the coldest measured surface in the solar system. Its surface is covered with nitrogen ice and has a thin nitrogen atmosphere, remarkably similar to Pluto. And Triton has active geysers. Voyager 2 images showed dark plumes erupting from the surface, nitrogen gas mixed with dark organic material venting from beneath the surface. The heating mechanism is thought to be solar. Transparent nitrogen ice acts like a greenhouse, allowing solar radiation to penetrate to a dark substrate below, which heats up and vaporizes the overlying nitrogen. Triton's geysers are a window into the geological activity of a large Kuiper Belt body. If Pluto, which we studied with New Horizons, shows nitrogen ice convection and atmospheric cycles, and if Triton, a captured Kuiper Belt object, shows active geysers and a thin atmosphere, then large Kuiper Belt objects as a class are geologically active worlds rather than passive, frozen remnants. This changes how we think about the Kuiper Belt as a whole. It is not a static graveyard of primordial material. It is a region containing dynamically and geologically interesting worlds. Let us now talk about the specific scientific question that the next decade of outer solar system research will focus on, about whether Kuiper Belt objects have subsurface oceans and what this would mean. Pluto may have a subsurface liquid water layer. This is inferred from several lines of evidence provided by New Horizons data. The alignment of Sputnik Planitia. The nitrogen ice plain is located on Pluto's hemisphere that always faces Charon, the sub-Charon hemisphere. This alignment is not random. It suggests that Sputnik Planitia represents a mass concentration, a region denser than average, that has reoriented to face Charon through tidal forces. A dense, nitrogen-filled basin could explain the mass concentration, but so could a local thickening of an interior liquid layer that has pooled beneath Sputnik Planitia. The lack of compressional features.
When water freezes to ice, it expands by about 9%.
If Pluto's interior froze from a primordial ocean, the expansion should have created compressional, thrust fault features on the surface. Instead, Pluto's surface shows extensional features, rifts and normal faults, consistent with expansion of the crust. This would be consistent with the presence of antifreeze, ammonia, in the water, which causes contraction rather than expansion when freezing. The depth and shape of some craters. Modelling of the relaxation of topography over geological time, how craters deform under the weight of the ice, is more consistent with the presence of a liquid layer beneath the ice than with an entirely solid interior. None of these lines of evidence is definitive on its own. Together, they form a circumstantial case for a possible subsurface ocean. If Pluto has a subsurface liquid water ammonia mixture, it likely extends to perhaps 100 to 165 kilometers below the surface. Maintained by radioactive decay in the rocky core, not by tidal heating as for Enceladus or Europa, since Pluto has no nearby massive body to provide significant tidal heating. This is remarkable. A world 40 astronomical units from the Sun, potentially harbouring liquid water, sustained for billions of years purely by its own internal radioactive heat. It implies that similar subsurface liquid layers could exist in any Kuiper Belt object large enough to retain significant radioactive heat. Any object larger than roughly 300 to 400 kilometers. There may be hundreds of ocean worlds in the Kuiper Belt. Not warm, life-friendly oceans like Earth's. Cold, pressurized, ammonia-rich, in permanent darkness. But liquid environments nonetheless. Environments where chemistry continues, where material cycles between the rocky core and the liquid layer, where complex organic molecules might form from the tholins and volatiles present.
We do not know if any of these putative Kuiper Belt oceans harbour or harboured life. We barely know whether they exist. But the possibility that the outer solar system is populated with hundreds of miniature ocean worlds, each with liquid water hidden beneath kilometers of ice, transforms the picture of the habitable solar system fundamentally. Let us now talk about the specific observation that most illustrates how active and surprising the outer solar system is, about the discovery of activity on Quaoar that was entirely unexpected. In 2023, alongside the discovery of Quaoar's anomalous ring, astronomers found evidence of cryovolcanic activity on Quaoar itself. Specific spectral features in Quaoar's near-infrared spectrum, obtained by JWST and ground-based telescopes, suggested the presence of crystalline water ice and ammonia hydrates on the surface.
This is significant because water ice at Kuiper Belt temperatures, 70 Kelvin, normally exists in an amorphous state, a disordered, non-crystalline structure. Converting amorphous ice to crystalline ice requires warming to about 130 to 150 Kelvin. At Quaoar's distance from the Sun, there is no external heat source capable of achieving this. The only plausible explanation: internal heat. Radioactive decay in Quaoar's rocky interior generates enough heat to warm the ice above the crystallization temperature at some depth. And cryovolcanic activity brings this material to the surface where we can observe it in its crystalline form before it has time to be reamorphized by radiation. Similarly, ammonia hydrates are unstable at Quaoar's surface temperature and radiation environment on timescales of millions of years. They should have been destroyed by UV photolysis long ago, if they had been there since Quaoar formed. Their presence implies recent delivery to the surface, again consistent with recent cryovolcanic activity. Quaoar, a 1,000-kilometre body that did not look particularly special before detailed spectroscopic observations, turns out to be geologically active today. Not dramatically active like Io, but active enough to be bringing fresh material from its interior to its surface. This finding adds to the emerging picture from Pluto, Triton, Charon and Arakoth that the outer solar system is not a passive deep freeze. It is a region of slowly active geology, different from the vigorous geological activity of Earth or Io, but real and consequential for the long-term chemical evolution of these worlds. Let us now talk about what the study of the outer solar system has contributed to our understanding of planetary formation in general, and specifically about what the size distribution of Kuiper Belt objects reveals. The size distribution of a population of small bodies, the number of objects as a function of their size, carries information about both how they formed and how they have subsequently evolved through collisions. For the Kuiper Belt, the size distribution follows a rough power law. For every factor of 2 decrease in size, there are roughly 4 to 8 times more objects. The exact slope depends on the size range. But there is a change in the slope at around 100 to 200 kilometers diameter, a knee in the distribution. Objects larger than this seem to follow a steeper size distribution than objects smaller than this. The interpretation? Objects larger than the knee diameter formed by direct gravitational collapse of particle swarms, the same mechanism that formed Arakoth. This process produces a specific size distribution. Objects smaller than the knee diameter are predominantly collisional fragments, produced by the disruption of larger objects in subsequent collisions. Collisional fragmentation produces a different size distribution. This bimodal origin, gravitational collapse for the large bodies, collisional fragmentation for the small, is now supported by multiple lines of evidence, including the Arakoth flyby result and theoretical modelling. For planetary science more broadly, this tells us that the dominant mechanism for forming planetesimals, the building blocks of planets, is not particle sticking through pairwise collisions, but gravitational instability of streaming concentrations of pebbles. This streaming instability mechanism, proposed theoretically in the 2000s and increasingly supported by observations, changes how we think about the earliest stages of planet formation throughout the universe. The Kuiper Belt, preserved from those earliest stages because it was never incorporated into a planet, gives us our only direct observational window into the size distribution imprinted by the initial formation process. It is a fossil record of planetary formation. Let us now talk about a specific technological development that will transform outer solar system exploration in the 2030s and beyond, about the role of artificial intelligence in autonomous spacecraft operations at great distances. The communication time lag between Earth and outer solar system spacecraft creates a fundamental operational constraint. At 40 astronomical units, the one-way signal travel time is about 5.5 hours. By the time a problem is detected from telemetry, a command response sent and confirmation received, more than 11 hours have elapsed. For a fast-developing anomaly, this is far too slow for ground-based intervention. New Horizons was designed with extensive autonomous fault protection. If specific anomalies were detected, the spacecraft could autonomously execute pre-programmed response sequences without waiting for ground commands. This autonomous capability was essential for the fast flyby operations at Pluto. The encounter geometry was changing so quickly that pre-programmed sequences executed without real-time ground intervention. Future outer solar system missions, orbiting Kuiper Belt objects, landing on their surfaces, operating in their environments for months or years, will need much more sophisticated autonomy than New Horizons possessed. Not just fault protection, but autonomous science decision-making.
Imagine a future lander on a Kuiper Belt object's surface. It has detected something unexpected, a fresh exposure of crystalline ice suggesting recent cryovolcanic activity nearby. Should it move toward the exposure? Move away? Continue the planned sampling sequence? The science team on Earth cannot weigh in for 11 hours.
The lander needs to make this decision autonomously, evaluating the scientific value of investigating the unexpected finding against the operational risks of deviating from the planned sequence, and acting in a way the science team would sanction. This requires artificial intelligence, specifically machine learning systems trained on the expected science objectives and operational constraints that can apply the team's values and priorities to novel situations encountered in the field. NASA's AEGIS, Autonomous Exploration for Gathering Increased Science system, already performs autonomous targeting on the Mars rover Curiosity, allowing the rover to identify scientifically interesting rock targets in its images and autonomously direct the laser spectrometer to them without human review. This is the beginning of a capability that will need to be much more powerful for outer solar system exploration. The development of autonomy for deep space missions is not just a software engineering challenge. It requires rethinking the relationship between human scientists and robotic explorers. How much do we trust autonomous systems to make science decisions? How do we ensure that autonomous choices align with the science team's actual priorities? How do we maintain meaningful human oversight and accountability for billions of dollars of scientific investigation? These questions are as much philosophical as technical. They will need to be answered before we can effectively explore the distant reaches of the outer solar system. Let us now talk about the specific legacy of New Horizons that extends beyond its scientific discoveries, about what it means for a mission to visit a world for the first time. Before July 14, 2015, Pluto was a mathematical abstraction, a point of light, a set of numbers, mass, radius, atmospheric pressure, albedo, inferred from distant observations. It was real in the sense that real measurements had been made of it, but it was not concretely real in the way that something you can see in detail is real. After July 14, 2015, Pluto is a place, a specific, detailed, visually comprehensible place with mountains and plains and atmosphere and weather patterns. A place where you could orient yourself. That is north, there is Sputnik Planitia, that jagged ridge is the Norgay Montes. The kind of specific, concrete reality that comes only from actually seeing something in sufficient detail. This transformation from abstraction to place is what first-time planetary exploration does. It happened with Mars in the Mariner missions, with the Moon in Apollo, with Jupiter and Saturn in the Voyager flybys, with the specific inner solar system bodies in a sequence of targeted missions. Each time a world is visited for the first time, it stops being an abstraction and becomes a place. And with that transition comes a cascade of new questions that only arise when the specific reality of the place is known. Questions that could not have been formulated before because they depend on details that were unknown. Before New Horizons, we did not know to ask about nitrogen ice convection on Pluto. We did not know nitrogen ice plains of such extent existed. We did not know to ask about the chemical connection between Pluto's atmosphere and Charon's Mordor region. We did not know Mordor existed. We did not know to ask about subsurface ocean indicators on Pluto. We did not have the data to pose the question in the specific form it now takes. The outer solar system still contains many worlds that are only abstractions, the hundreds of known Kuiper Belt objects that are only points of light in telescope data. Each of them is a place in the same sense that Pluto is a place, but a place we do not yet know.
Each one visited for the first time will become concrete and specific, and will generate new questions we cannot yet formulate. This is the scientific case for continued outer solar system exploration. Not just that we will find new facts about known phenomena, but that we will encounter specific realities that transform our entire framing of the questions. Let us now talk about what is perhaps the most mind-expanding single fact about the outer solar system, about the relationship between the Oort Cloud and galactic structure. The Sun orbits the center of the Milky Way galaxy once every approximately 225 to 250 million years, at a speed of about 220 kilometers per second. As the Sun moves through the galaxy, it occasionally passes closer to spiral arms, regions of higher star density and higher star formation, through the galactic plane and back, and occasionally close to individual stars.
The Oort Cloud, extending to perhaps 200,000 astronomical units, or about 3 light years, is so large that it is genuinely affected by the galaxy's structure. The differential gravitational force across the Oort Cloud from the galactic center, the galactic tide, is a real astronomical force with measurable effects on Oort Cloud orbits. Over the 225 million year galactic orbital period, the Sun moves through varying density regions of the galaxy. When the Sun passes through a denser region, spiral arm, for example, the rate of stellar encounters close enough to perturb the Oort Cloud increases. This increases the rate of comets injected into the inner solar system. Some researchers have proposed a connection between the Sun's galactic orbit and the timing of impact-related mass extinctions on Earth. The idea, as the Sun passes through galactic spiral arms periodically, the increased perturbation of the Oort Cloud sends enhanced comet showers into the inner solar system, elevating the impact rate, causing mass extinctions. The roughly 26 million year spacing, sometimes claimed for mass extinctions in the fossil record, has been compared to proposed periodicities in the Sun's galactic orbital dynamics. This proposed connection remains controversial. The timing of the Sun's spiral arm passages and the timing of mass extinctions are both imprecisely known, and the statistical case for a periodic mass extinction signal is debated. But the physical mechanism is real. The galactic tide does influence Oort Cloud dynamics, and the rate of comet injections does depend on the galactic environment. The implication is profound. The history of life on Earth has been influenced by our location in the Milky Way galaxy, by the Sun's orbit through the galactic disk, by the gravitational tidal forces of the entire galaxy acting on the most remote corners of our solar system. We are not isolated. Our biology has been shaped by galactic dynamics. Let us now talk about a specific current research program that is directly testing models of Kuiper Belt formation through careful statistical analysis, about the OSOS survey and what it taught us. OSOS, the Outer Solar System Origins Survey, was a large-scale survey of trans-Neptunian objects conducted from 2013 to 2017 using the Canada-France-Hawaii telescope. It was designed specifically to address observational biases that plague other Kuiper Belt surveys. The key insight behind OSSOS: most Kuiper Belt surveys find objects by pointing telescopes at specific parts of the sky, often the ecliptic plane, which is most efficient for finding solar system objects. But this creates a systematic bias. Objects on inclined orbits or in other parts of the sky are undersampled. OSSOS used a carefully designed survey strategy with precise tracking of which parts of the sky were observed and with what depth. This allowed the survey to characterize its own biases precisely and then correct for them when analyzing the orbital distribution of discovered objects. The result one of the most unbiased samples of the Kuiper Belt ever obtained. The orbital distribution of OSSOS detected objects, corrected for observational biases, provides a clean view of the true dynamical structure of the Kuiper Belt. Several key findings from OSSOS. The population of classical Kuiper Belt objects has two components with different orbital properties: a dynamically cold component, low inclinations, nearly circular orbits, and a dynamically hot component, higher inclinations and eccentricities. These two components likely have different formation histories. The cold component probably formed in place at 40 to 48 astronomical units. The hot component was likely scattered outward by Neptune's migration. The abundance of Plutinos, objects in 2 to 3 resonance with Neptune, is consistent with models of Neptune's outward migration, but with specific constraints on how fast that migration occurred. A faster migration produces more Plutinos trapped in resonance. A slower migration produces fewer. The distribution of scattered disk objects is consistent with ongoing scattering by Neptune. New objects are being placed on scattered disk orbits today as Neptune's gravity deflects Kuiper Belt objects. The extremely distant objects, those with large perihelia, Sedna-like objects, remain statistically anomalous even when OSSOS biases are corrected. The sample is small, but the clustering of their orbital parameters, which motivated the Planet 9 hypothesis, appears to survive careful bias analysis. OSSOS represents the state-of-the-art in careful, bias-corrected Kuiper Belt surveys. The Vera Rubin Observatory's LSST will produce a survey thousands of times larger in terms of detected objects, with similarly careful characterization of observational biases built into the design from the start. Let us now talk about the specific observation you can do tonight that directly connects to the themes of this conversation, about finding a comet if one is visible, and what that means in the context of everything we have discussed. The sky at any given time may or may not have a naked eye or binocular comet visible. Comets are unpredictable in their brightness. A comet that was predicted to be spectacular sometimes disappoints, and occasionally a comet appears unexpectedly bright. If a comet is visible, finding it and looking at it even through binoculars gives you direct visual access to a body from the outer solar system. Most periodic comets come from the Kuiper Belt or scattered disk. Long-period comets come from the Oort Cloud, from distances of thousands to tens of thousands of astronomical units. When you look at a comet, you are seeing the nucleus, too small to see directly for almost any comet visible to naked eye or binoculars, but the source of all the activity. A nucleus of perhaps 1 to 10 kilometers of dirty ice, water, carbon dioxide, carbon monoxide, and organic compounds, frozen together since the early solar system. The coma, the diffuse cloud around the nucleus, formed as the nucleus heats and outgasses. The gas and dust expand away from the nucleus in all directions, producing the fuzzy appearance. The tail, or usually two tails. The ion tail, blue-white, pointing directly away from the Sun regardless of the comet's direction of motion, is gas ionized by solar ultraviolet and pushed away by the solar wind. The dust tail, yellowish-white, curving slightly, is dust pushed by sunlight, following a slightly curved path as the dust grains of different sizes respond differently to radiation pressure. Everything you see in a comet is material that has been frozen for 4.6 billion years in the outer solar system, in the Kuiper Belt or Oort Cloud, and is now being liberated for the first time, or one of the first times, as the comet passes near the Sun. The organic molecules in the coma, the tholins, the amino acid precursors, the complex hydrocarbons, are the same class of chemistry that possibly seeded early Earth, with the building blocks for life when comets bombarded the young planet. You are looking at ancient outer solar system chemistry undergoing its first transformation in billions of years. That is what a comet is. Let us talk about one more specific thing that makes the space beyond Neptune stranger than most people appreciate, about the timescales on which everything there operates, and what those timescales mean for how we understand this region. Pluto orbits the Sun once every 248 years. This means that since Pluto was discovered in 1930, it has completed less than a quarter of one orbit. We have watched it for less than a quarter of 1 year of its life. The nitrogen ice convection on Sputnik Planitia, the slow overturning of nitrogen ice cells we observed in the New Horizons data, operates on timescales of tens of thousands of years per complete convective cycle. Sedna orbits the Sun once every 11,400 years. In the time since the last ice age ended on Earth, roughly 12,000 years ago, Sedna has barely completed one orbit. In the entire history of human civilization, roughly 5,000 to 6,000 years of recorded history, Sedna has moved through less than half an orbit. The objects in the Oort Cloud have orbital periods of millions to tens of millions of years. A comet now approaching the Sun from the Oort Cloud began its journey inward millions of years ago, when our ancestors were not yet recognizably human. This is a different kind of time from the geological timescales we invoke when thinking about Earth's history. Geological time is long, billions of years for the oldest rocks. But geological processes on Earth happen continuously, and the Earth we see today has been shaped by those continuous processes acting over long times. The outer solar system operates on orbital timescales. Things happen once per orbit, and orbits are thousands to millions of years long. A comet from the Oort Cloud passes through the inner solar system perhaps once in its entire existence. A Kuiper belt object on a stable orbit may be perturbed significantly only once every billion years. This means the outer solar system carries an almost unimaginable depth of history, not recorded in geological strata that get recycled and overprinted, but preserved in orbits and in chemically frozen surfaces that have barely changed since they formed. Arakoth's surface chemistry, those tholins and mixed ices, has been accumulating for 4.6 billion years with essentially no interruption. When New Horizons flew past it on January 1, 2019, it was seeing material that last saw significant change in the early solar system. The orbits of the objects in the Kuiper belt carry the gravitational memory of Neptune's migration billions of years ago. The orbital distribution of long-period comets carries the memory of stellar encounters that occurred when the solar system was part of a birth cluster. The outer solar system is deep time made physically accessible, not through fossils and rock layers, but through the positions and compositions of objects that have preserved their primordial states across the entirety of solar system history. This depth of preserved history is precisely why it is scientifically irreplaceable. We cannot go back in time to study the early solar system, but we can go outward to a region where time has effectively been standing still since the beginning. That is what makes the space beyond Neptune worth understanding. Not its extremity, not its strangeness, not even its possible relevance to the question of life, but that it is the past, preserved and waiting. Go outside tonight, find south, or the direction where the stars of Sagittarius are visible low on the horizon. There, right now, is Pluto, a faint point of magnitude 14, invisible to the naked eye, requiring a good telescope. But it is there, 5 billion kilometers away.
The Sun's light takes 4.5 hours to reach it. New Horizons flew there for 9.5 years, and what it found when it arrived changed everything we thought we knew about the outer solar system. Pluto was supposed to be a frozen dead world, a dark, featureless sphere drifting at the edge of the solar system, a geological relic, a leftover. Instead, mountains of water ice 3 kilometers high, a plain of nitrogen ice the size of Texas, slowly convecting in cells several kilometers across, driven by heat from deep within the planet. A thin nitrogen atmosphere cycling between frozen and gaseous states as Pluto moves through its 248-year orbit. Dark reddish organic compounds covering much of the surface. Tholins, the same complex molecules that form when ultraviolet radiation and cosmic rays process simple ices. Molecules containing carbon and hydrogen and nitrogen in arrangements that are the chemical ancestors of amino acids. And Charon, half the size of Pluto, orbiting in permanent mutual lock so both worlds always show the same face to each other, with a dark red polar cap of tholins deposited from Pluto's escaping atmosphere. A planet painting its moon with organic chemistry. This is what we found at the edge of the Kuiper Belt. Behind Pluto, farther in the same direction, Arakoth. A snowman-shaped contact binary, two lobes that merged so gently billions of years ago that they left no mark of impact. A surface of reddish-brown tholins frozen since the early solar system. Untouched, unchanged. The most pristine sample of primary solar system material we have ever seen up close. Beyond Arakoth, Sedna. Moving slowly at 84 astronomical units right now on an orbit of 11,400 years, with a perihelion so far from Neptune that standard models of solar system dynamics cannot explain how it got there. Pointing towards something we do not understand, a stellar encounter in the early solar system, or the gravitational influence of an undiscovered massive body, possibly Planet 9. An object 5 to 10 Earth masses on a distant elongated orbit, possibly there, possibly not. We do not know yet. And beyond all of that, the Oort Cloud, never directly observed, known only through the long-period comets it sends us as messengers, extending nearly to the nearest stars. So vast that the Oort clouds of neighbouring stellar systems may overlap, allowing material to pass between them, allowing the chemistry that formed here to migrate there and back. The space beyond Neptune is not what most people imagine when they think about the outer solar system. It is not empty, it is not silent, it is not dead. It is a region of slowly moving bodies carrying the chemical memory of 4.6 billion years. Bodies whose surfaces have been accumulating radiation-processed organic chemistry since before Earth existed. Bodies that may harbour liquid water beneath their ice, not from stellar warmth, but from their own internal radioactive heat. Bodies that periodically send fragments of themselves into the inner solar system as comets, and those comets have been delivering their organic cargo to Earth for the entirety of Earth's history. The tholins on Pluto's surface, the same class of chemistry as on Arakoth, on Centaurs, in cometary Comae, when hydrolyzed, produce amino acids in the laboratory, the same amino acids that form proteins, the same proteins that form life.
We are made of chemistry that began in the cold outer solar system and was delivered here by comets. The carbon in your body, the nitrogen in your DNA, the complex organic molecules in every one of your cells, the precursors to all of this were processed in the outer solar system and carried inward. The space beyond Neptune is not distant from you. It is your chemical past, and it is still there, still dark, still cold, still producing tholins on the surfaces of hundreds of thousands of icy bodies on orbits lasting centuries to millennia, still sending occasional comets inward to remind us it is there. In the next decade, JWST will produce detailed spectra of hundreds of Kuiper Belt objects, revealing their chemical compositions in unprecedented detail. The Vera Rubin Observatory will find tens of thousands of new Kuiper Belt objects, building the statistical sample needed to understand the full dynamical and chemical structure of this region.
One of these surveys may find Planet 9, or may conclusively show it does not exist. Future missions, not yet funded, not yet designed in detail, will return samples from Kuiper Belt objects, will orbit dwarf planets, will answer whether Pluto's subsurface ocean is real and whether it could harbour life. The outer solar system will be better known in 2050 than it is today, in the same way that it is better known today than it was in 1992, when the first Kuiper Belt object was found. The revolution in understanding this region has barely started, but right now, tonight, it is just a direction in the sky. Find Sagittarius. Pluto is there, invisible to your eye but present, moving slowly through its orbit, its nitrogen ice convecting in cells that turn over on timescales of millions of years, its atmosphere cycling between ice and gas, its surface carrying the chemical record of the beginning. Behind it, Sedna, moving almost imperceptibly, one orbit every 11,400 years. Right now, on this specific night, it is at a specific point in that orbit that it has been at only once before in all of recorded human history. Behind Sedna, in the direction of the Oort Cloud, extending almost to the stars, billions of icy bodies that have never been seen and may never be seen directly. Each one a chemical archive, each one a potential future comet, each one a piece of the story of how the solar system formed and how its chemistry eventually produced life on a small rocky planet 40 astronomical units inward. The space beyond Neptune is worse than you think. Not darker, not more hostile, not more dangerous, more complex, more populated, more ancient, more chemically rich, more connected to the question of who we are and where we come from than its cold darkness suggests. Look toward Sagittarius. That is where 4.6 billion years of history is being preserved in the dark, waiting for us to come and read it.